The next talk is given by Ben Mikek, and it's about mutual refinement of context-free language reachability.
Hello, everybody. I'm Ben Mikek, and I'll be presenting mutual refinements of context-free language reachability. This is a work by Shuo. I'm presenting it for him because, unfortunately, he couldn't be here today. So I'll do my best to be a maximal under-approximation of what Shuo would have said today. And this is work at Georgia Tech with both of our advisor, Qirun and Zhang. So I'm going to structure this talk by giving first some background on the formal language reachability problem. Then we'll talk about the existing approaches. Then I'll introduce mutual refinement, which is our novel approach to solving the problem. And then we'll discuss some experiments that show the power of mutual refinement. And finally, we'll close with some discussion of future work. So context-free language reachability is a widely used program analysis framework that can be used to encode many different program analysis, static analysis problems. So we start with a program and some property we're interested in verifying, and it could be really anything you're interested in. And one strategy for answering this problem is to translate the program into a graph and the program property into a graph property. So depending on the particular analysis we're most interested in, this could be one of many different types of graphs. It could be a control flow graph, a value flow graph, lots of different possibilities. And the strategy is going to be then, if we have some property of the program that we're interested in, some static analysis query, we want to translate that into a query on the graph, and in particular into a question in the form of reachability. So we're interested in whether one node can be reached from another in the graph. However, it's not just a question of reachability in the graph. We impose an additional constraint on it, which is that the path, that we only are interested in certain paths in the graph. And in particular, we're going to label each edge in the graph with an element of some formal grammar. And then we're only interested in reachability along paths for which the labels of edges in that path form a string that is generated by the grammar that we specify. And through this, this is formal language reachability, and we can use this to express many different program analysis properties. So as an example, if we just have this two-line program where we assign AF from source, and then we assign sync from A.G, we can generate a very simple program for this that looks like this, where we have nodes for each of the values. And then the edges are labeled with these brackets that are labeled with F and G. And in this case, we have the semantics of the program are represented in this graph on the right. And finally, we have to specify a language. So in this case, this is called a Dyke language, where we have matching pairs of parentheses. But in general, we could have any kind of CFL we want to as labeling these edges. So in this case, in a Dyke language, we're interested in paths being reachable if the labels along the paths have paired parentheses, or in this case, we represent them with brackets. And in this particular example, that is not true because we have an open bracket with F and a closed bracket with G label, so the sync is not reachable from the source in this example because the path isn't generated by this Dyke grammar. Now, there's a well-known algorithm to solve the context-free language reachability problem in cubic time. There's been work on this going all the way back to 2000. But there are some program analysis problems that require more complex former grammars that are not CFLs. And that's where we get into why mutual refinement may be useful. So let's take as an example a taint analysis where we want to have both context sensitivity and field sensitivity. So in this case, we're going to represent this by interleaving two different CFLs, one for each of those two parts. So for context sensitivity, we have the CP language, which I'm going to refer to as the parenthesis language. And for field, that's a Dyke language. It's just paired parentheses. And for field sensitivity, we have the CB, which I'll call the bracket language. And that consists of either paired brackets or unpaired open brackets, but we can't have closed brackets that aren't paired with something. So both of these are CFLs. The second one isn't a Dyke language. And in interleaving them, what we're interested in is paths along the graph which form strings that can be generated by each of these grammars separately. So we're interested in the interleaving of these two grammars, and the interleaving of these two CFLs is not a CFL. And in fact, in work in 2022, it's been shown that the reachability problem for formal languages that are not CFLs is undecidable. And even, in fact, just interleaved Dyke languages, reachability in that context is also undecidable. And so every solution to this problem will be inherently an approximation. And what we're interested in is, can we improve upon the approximations? So I'll start by talking about what's the current approach to doing this, and then we'll talk about how mutual refinement can improve on that approach. So we have this example graph, which is in the two languages I described before, the parenthesis language and the bracket language. And we're going to use the two CFLs to over-approximate the reachability here by essentially performing reachability analysis one at a time. So in the first case, first we'll run the parenthesis language, and so we're going to trace all of the edges that contribute to reachability between any pair of vertices under the parenthesis language. So if we do that, for example, in this purple line, I've marked the path from S to T, and the purple line shows that T is reachable from S in the parenthesis language because we just have the paired open and close parentheses 22. In addition, for example, A is reachable from S because actually for the parenthesis language, that's just an empty string because we aren't interested in the interleaving yet. If we do this analysis separately for the bracket language, CB, T is also reachable from S along this red path that you can see. I'll note we have a paired brackets for second between S and A and P2 and ret2. And then we also have an open-only bracket, which remember is possible in the bracket language here. So T is reachable from S, and there's also some other pairs that are reachable, like ret2 from S. And so the traditional approach to solving this problem would be to take the intersection. So we run reachability in each language separately, and then we take the intersection of the reachable pairs that we found before. So in this case, in particular, T should be reachable from S because it's reachable in both languages. But there's a problem here. This is a false positive. Why is it a false positive? Well, the path from S to T that's valid in the parenthesis language, the one marked in purple, well, it's not valid in the bracket language because it has an unpaired closed first bracket. And the path that's valid in the bracket language, it's not valid in the parenthesis language because we have an unpaired open parenthesis 25. And that means that this running CFL reachability on each language separately and then intersecting them can produce false positives, so it's not very precise. And our idea is to iteratively modify the graph by removing edges in order to solve this problem. That's mutual refinement. So the general approach is we start with the original graph, we run a modified version of reachability, in this case for the bracket language, but for whatever our first CFL is, to produce a smaller graph. So we remove any edges that don't contribute to reachability between any pair of vertices. Then we do the same thing for the next language, in this case for the parenthesis language, to produce an even smaller graph, G prime prime. And we do this iteratively. That's the key thing. So we run each language one at a time, we remove edges one at a time, and we run this process iteratively until we reach a fixed point. And that's how mutual refinement differs from the original approach. We're doing this edge collection at each step instead of just taking an intersection at the end. So I'll talk a little bit more formally about how mutual refinement works. In traditional CFL reachability, we have kind of the first part here, which is tracing edges. So the approach is to trace the edges that contribute to reachability between pairs of vertices, and then we can come up with a set of pairs of vertices that are reachable from each other. What's different in mutual refinement is the edge collection process. So we still do tracing for each language in each round, but then we collect the edges and mark them. And I think the easiest way to think about that is if we were removing them from the graph. But that's more kind of a way to think about it more than an actual implementation. So the process is we trace for each CFL, one for each CFL in each round. We collect the edges that are relevant to that, and we do this iteratively until we reach a fixed point where the edge set doesn't change anymore. So this is very abstract, and I think the best way to think about this further is with a more concrete example. So we'll return to this same program that originates from a taint analysis problem. And we're going to show how mutual refinement can solve the false positive that we saw before. The languages are the same, the parenthesis language and the bracket language. So in the first round, we're going to trace, arbitrarily, we're going to decide to start with the bracket language here. And so what edges don't contribute to reachability between any pair of vertices in the bracket language? Well, the closed bracket between P1 and ret1 is like that, because it doesn't have a pair. It's not contributing to reachability between P1 and ret1 or any other pair of vertices. And so we can remove that edge. We collect it and remove it from the graph. Next, we do the same thing with the parenthesis language. So we're going to trace all of the edges that don't contribute to reachability between any pair in the parenthesis language. And this is where we really start to see the benefit of mutual refinement. Because now, open parenthesis 22 and closed parenthesis 22 along the top, neither of those contribute to reachability between any pairs any longer because we removed the edge in the middle. So both of those can now be removed. And in addition, this open parenthesis 25 along the bottom path can also be removed. Now we run a second round, again starting with the bracket language. And now, because we removed that edge from A to P2, the closed second bracket in the bottom path also doesn't contribute to any reachability, so it can also be removed. And now I think we can see that neither of these two parentheses that are left contribute to any reachability because we've removed the path that connects them. So they can also be removed. And now let's suppose we wanted to do a third round of this. Well, if we wanted to remove another, if we were tracing brackets again, we only have open brackets left. And remember, in the bracket language, open brackets are fine, so they contribute to reachability between S and A or between X and T, for example. If we did tracing for parentheses, well, there are no parentheses left, so certainly we can't remove any more edges, which means that if we ran another round of this, we wouldn't change the graph, and we've reached a fixed point. And from this graph, we can quite quickly conclude that T is not reachable from S. And through mutual refinement, we've removed the false positive that was identified through the traditional approach of tracing and then intersecting. In the paper, we've proven two theorems about this mutual refinement process. The first is that it always reached a fixed point, and in fact, that fixed point is unique. So no matter which order we apply the individual CFL approximations in, you will always reach the same fixed point where you can no longer collect any other edges from the graph. And second, mutual refinement is guaranteed to be at least as precise as the traditional intersecting approach. So no matter what, if you find a false positive with mutual refinement, that will also be a false positive in the traditional intersecting approach. And there should be some false positives that you removed by switching to mutual refinement. These are two important facts about mutual refinement. We also considered the complexity. So traditional CFL reachability has cubic time complexity and quadratic space complexity. And mutual refinement has no worse time complexity. It's also cubic. Both the tracing and edge collection are each cubic, so the overall process is cubic. It does have cubic space complexity, which is asymptotically more than the traditional approach. But for time at least, it doesn't take, it asymptotically takes the same amount of time as the traditional approach. And V here is the number of vertices in the graph. And so with that, I'll talk, so we've seen that mutual refinement is more precise, is at least as precise as the traditional approach. In addition, we've seen that it has no worse asymptotic running time, but we think that in practice, it should have higher precision and probably not much worse running time. And so we've set out to show that with experiments. And in the paper, we show experiments with two different client analyses. The first is a taint analysis for Android apps written in Java. And this is over-approximated using two CFLs. The second is a value flow analysis that comes from Spec 2017 CPU benchmarks that have been compiled into LVMIR. And this is over-approximated with 3 different CFLs. The baseline is the traditional approach I showed you at the beginning, which is to trace reachability with each language separately and then intersect the results. And the comparison is mutual refinement, so the process we just saw. The benchmarks are quite large, so there are several that have more than 100,000 vertices and edges. And there are 2 benchmarks, one for taint analysis and the other for value flow analysis. And indeed, mutual refinement does improve the precision. So for taint analysis, we saw precision improvements of, on average, 50% over the entire benchmark set. And for the value flow analysis, precision improvements of about 10% over the entire benchmark set. And this comes with some overhead, as we saw, so asymptotically, mutual refinement isn't any worse than the traditional approach, but in practice, it takes about 2.5 times as long for these benchmarks, and it uses about 3 times as much space. And in this case, we're measuring precision by the total number of reachable node pairs. So if we reduce the number of false positives by some extent, then that's what's being shown in the precision improvement column here. There are a couple of interesting points to make here. So first, I mentioned that we've proven that a unique fixed point exists for mutual refinement and will always converge to that unique fixed point, regardless of the order in which the CFLs are applied. However, choosing a different order of application for the CFLs in each round may affect how quickly we converge to the fixed point. So that's something for future work to consider how to come up with a heuristic to pick which order to apply the CFLs in to speed up convergence towards the fixed point. In addition, in practice, if we know a little bit more about the problem and we aren't interested in just computing reachability for all pairs, then we may not need to run all the way to the fixed point. If we're just interested in a single pair, for example, then we can ignore all of the other edges and only focus on paths that connect the two nodes we're interested in. And if we know other information about the particular problem we're interested in, we may be otherwise able to stop mutual refinement before it reaches the fixed point, thereby improving performance. And finally, there's a previous work on fast graph simplification for interleaved dike reachability. And it's important to distinguish what we do here from that work because mutual refinement can apply to interleavings of any CFLs. And in fact, it can apply to any formal language because at each step in mutual refinement, we run trace using each different CFL, but those CFLs need not be the exact definition of the formal language we're interested in. They could be over-approximations. And so we can, as long as we can represent the formal language as interleaving of over-approximating CFLs, which you can do for any formal language, then mutual refinement can apply. Okay. So in conclusion, we propose mutual refinement. This is a novel strategy for performing reachability in graphs under formal language reachability in graphs. And it allows us to improve the precision compared to previous approaches. And we prove the existence of a fixed point for mutual reachability. So we show theoretically that it will always reach a fixed point and the order of application of CFLs doesn't matter for that fixed point. And then finally, through our experiments, we show that in fact there is a very great practical improvement in precision. And there's some overhead, but asymptotically, mutual refinement doesn't perform any worse than the traditional intersecting approach. And so with that, thank you for your time, and I'd be happy to take any questions.
So do we have questions in the audience? Yes?
Thank you for the talk. Just a curiosity connected to the conclusion. Have you thought about maybe not starting from context-free languages, but from like more expressive languages, not context-sensitive, maybe, I don't know, index languages, and applying the your algorithm to this kind of language? I don't know.
Yeah, that might be interesting future work. I think, so as long as you can, any formal language, you should be able to over-approximate by interleaving CFLs. So in that sense, you can already apply mutual refinement to it. Whether you could do the same type of strategy with a subset of some particular class of formal languages, it might be possible. I guess you'd have to, so that the tracing right now we take from kind of existing work on CFL reachability. So if there were a good process for tracing for your particular class of languages, then certainly you could apply mutual refinement to it.
Other questions? Okay. Do we have questions on Discord?
Thanks for the talk. So maybe it's building on the last one a little bit, but like, can you, I mean, so like, can you think about maybe some generalizations that will allow you to apply the mutual refinement in some more general context with, you know, richer domains or something like this, or just speculate?
Yeah. So I think, I guess there are two parts to that. The first is, so I think mutual refinement could be used to represent anything right now. It just probably wouldn't be very precise, right? So I think it's mostly a question of can we improve the precision by doing better in each round. And so I think in the general strategy, yes, definitely could be generalized. And really, whatever strategy you have for tracing edges should be possible to apply within mutual refinement, really almost without any limits on what it does. So as long as you have a method of tracing which edges contribute to reachability based on whatever criteria you're interested in, mutual refinement will probably perform better than just running whatever process you have on the whole graph and intersecting the results.
Okay, so thank you very much.